Okay, so this is a lesson on Euler's number. Everyone go ahead and turn to page 33 in your packet and get started on number 1. Pause the video and unpause it when you're ready. Okay, so Ron is going to deposit $1 into an account at eBank. eBank offers an APR of 100%. That's amazing. Ron believes that he will have $100 in his account at the end of 1 year if interest is compounded at smaller intervals of time. And we are supposed to write a formula that Ron can use to compute the future value of the account after 1 year if the interest is compounded n times per year. So we are going to use our formula for future value. So we're going to start with his amount will equal, well, his principal is just $1, so we're just going to put a 1 here. And then we've got 1 plus, and he's getting 100% interest, so that's fabulous. I'm going to put 1 up here because that's 100 as a decimal. And we're going to compute n times per year, compounded, sorry, n times per year. And so we're going to raise it to the power nt is just going to be n, and then number of years is just 1. So here's the formula we're going to use. Part B says, compute the future value of the account after 1 year for several compounding periods. Let's see what we got. So we've got yearly, semi-annually, quarterly, monthly, weekly, daily, hourly, and every minute. So here we go. First off, yearly is going to be just once. Semi-annually will be twice, 4, 12. Weekly would be 4, 52. Then daily would be 365. Hourly, if I multiply that times 24 hours in a day, would be 8,760. And every minute, multiply again, number of minutes in a year. Oops, that's a 2, 5, 600. Now, future value. So basically, I'm just going to put this n number up into my formula. So the first one's pretty obvious. If it's 1 plus 1 over 1, that becomes 1 plus 1 is 2 to the first power. So it's like 1 plus 1 over n times 1. That's just going to be 2. No big deal. Then we've got 1 times 1 plus 1/2 raised to the 1 times 2. I'm going to stop writing this 1 times 1 because that's kind of redundant. And I do that on my calculator and I'm going to get 2.25. And I'm going to keep doing this. So go ahead, you gotta pause the video if you need to. So now I'm going to do 1 plus 1 over 4 to the 4th power and so on. Go ahead and finish that up. And there you should get the following future values. Okay, so once we have these future values, the next question we have on page 33 is how would you describe what is happening to the value in this account? Well, if we're only getting our 100% interest once a year, our $1 just becomes $2. Semi-annually earns us an extra 25 cents. Quarterly earns us an extra 44 cents and so on. But once we switch from hourly to minute, even though there's a big jump in the number of times being compounded, we're still just getting $2.72 from our investment. So I would guess if we went to every second, which would be like crazy, that would probably also give us 2.72. So I would say the future value is approaching $2.72 as we compound more frequently. Okay, then number 3 says, will the future value of the account ever reach $100? Why or why not? Well, we kind of already answered that. We found out that even if we compound very, very frequently, we're only going to have $2.72. So the answer is going to be nope, even compounding every minute only gives us $2.72. Excellent. So everyone go ahead and turn the page. So now we are actually going to, ooh, whoops, page up. Scratch that, don't turn the page. Oh, we missed something. I thought we had. So what is the significance of the value of the account after 1 year as n gets larger and larger? Well, the significance is, if I take that formula, and just as a reminder, that formula as the amount equals 1, and then it was 1 plus 1 over n to the 1 times n. As we have this formula and n gets really big, like it approaches infinity, the amount is approaching $2, well, not really $2.72, but $2.72. And what this leads us to is the value of n. So as it gets larger and larger, we are approaching this number. You guys need to write this down. Like, this is important. You need to write this down. Okay? As this formula gets larger and larger, 1 plus 1 over n raised to n is approaching e. This is a number. It's called Euler's constant. We say that this number e is an irrational number. It cannot be expressed as a fraction. It's kind of like pi or the square root of 2. It is an irrational number. But we are going to use Euler's number a lot in the real world because Euler's number represents continuous growth. You have to imagine if we were getting interest on our $1 all the time, we still would only have 2.72. So if we had something that was doubling, compounded continually, if you started with 1, after 1 year you would have 2.72 if it doubled every year but compounded continuously. So let's make a little note. Euler's constant is used for continuous compounding. Now, it doesn't mean that something's like getting like really giant extremely fast. It just means that its growth is not in an interval. It happens continually. It's not like boom, the bunnies magically double. It's that the population is growing over time. So what we're going to do is we're going to now compare the graphs of some exponential functions using Euler's constant to some of our parent exponential graphs we've done so far. So go ahead and turn to page 34. Okay, so it says graph each function f and g and complete the table of values below. Describe the key features of the graph. So you may want to use your calculator for this, or honestly, I'm going to do it without a calculator because sometimes I get confused when I use my calculator and I don't really need to. I want to remember that E is approximately 2.7. That's going to be the estimation I use for these graphs because that will be specific enough. So when I fill in this table, e to the negative 1 power is just 1 over 2.7. E to the 0, well, 2.7 to the 0 is 1. E to the first is 2.7. And then E squared, well, 2.7 is close to 3. 3 squared is, I bet it's close to 9. Let's find out. So E, in case you were wondering, is second, and then it's above ln, and it gives you the little box. So I'm going to go, if I just go squared, I get 7.4. And just to show you what I mean there, so if I go with 2.7 squared 7.3. And if you just, and I wanted to point out, e is also above division, and that e does not give you a exponent. So there's our 2.7. All right, so if we go to graph this function, we've got 0, 1. We've got 1, 2.7. Notice each square is worth a half. So it's like here. We've got 2, 7, so we'll say 7.4 is like here. And then we've got negative 1, let's see, 1 divided by e is approximately 0.4. And here's, from this point, I can get my curve. Just like an exponential function, I'm going to have a dotted asymptote. Okay. So, I have this function. Its domain, just like the exponential growth curve next to it, has a domain of all reals. It also has a range of y is greater than 0. Hey, it has an x-intercept, an asymptote of y equals 0. It does not have an x-intercept. It does have a y-intercept of 1. And this graph is always increasing. This is not surprising because this base e is just 2.7. It's like y equals 2.7 to the x. And this is just 2 to the x. So they're very similar. I'm going to take a look at page 34. So on 34, you've got a similar situation, but now we've got e to the negative x. So remember, that's like e is about 2.7. So 2.7 to the negative x. So if I've got e to the negative 2 from my last page, I remember that that's 7.4. E to the negative 1 is going to just be e. E to the 0 is 1. E to the first, well, e to the negative was 0.4. I'm just remembering these values from the last page. So when I graph this, it's going to look similar. I'm still going to have that y-intercept, but now it's going to be a decay function. So that's 3, so 2.7 is like here, and then negative 2 was 7.4, which is right here, and oops, I missed. I'll pretend that it goes to that point. I don't know why I can't hit it. Promethean problems. And then here's my asymptote. And so next to it, I've got a comparison graph. I've got the graph of 2 to the negative x, which remember is just like 1/2 to the power of x. And I'm going to have a lot of the same properties. I'm still going to have a domain of all real numbers. I'm still going to have a range greater than 0. I'm still going to have an asymptote of y equals 0. No x-intercept, a y-intercept of 1, but now this function is decreasing. Okay, why don't everyone try... Okay, so this is not in your packet. It's a little something we're also going to do the same day we're doing Euler's number, so just write this down somewhere. It says solve each equation correct to 3 decimal places, graph it to support your calculator work. So before we learn how to solve these kinds of equations algebraically, I'm going to show you how to solve them graphically. So if we're solving number 1, the first thing we can obviously do is divide by 2. And we get 3 to the x equals 4. Now, there's nothing else we know how to do yet to solve this equation. So what we're going to do is we're going to utilize our graphing calculator. We're going to put 3 to the x in y1, and we're going to put 4 in y2. So I'm going to go to my calculator, I'm going to turn it on. Oh, there we go. So I've got 3 to the power of x, and then I'm going to just put 4 in y2. I'm going to take a look at my graph. And I see I've got my exponential curve and I've got a line. So I'm going to recopy that right here. So there's the line at 4. I should probably made that a little thicker so you can see it better. There's my line at 4. And then I've got the curve. Looks like it's got a y-intercept of 1 because 3 to the first would be 1, or 0. 3 to the 0 would be 1. 3 to the first would be 3. 3 squared would be 9, which is a little off my curve, and my curve would just fit in like this. And you can see that this graph, this purple graph, is going to intersect the line just like it does over here on my calculator. So now what I'm going to do on my calculator is I'm going to press second, trace, and I'm going to pick the command number 5, intersect. Okay, so I'm going to go second, trace, and I'm going to pick number 5, intersect. And so because I only have 2 curves here, I could just press enter. But I want you to notice for first curve, my first curve is my exponential curve, and there it says y1 equals 3 to the power of x, so I'm just going to press enter. Second curve, you can see that it jumped to y2 equals 4, so I'm going to press enter. And then for guess, I want it to give me this point where they cross, so I'm going to move my arrow and kind of guess where it is. You don't have to do this if it only crosses once, but I'm going to. I'm going to press enter. And I find that these 2 graphs will intersect when x equals 1.262, because it says 3 decimal places. So I want to show you something. If I go back to my home screen and I type in 2 times 3 to the power of 1.262, I should get about 8. Yep, about 8. So I found the correct exponent that will work in this equation. And this is how we're going to solve these until I teach you how to solve them algebraically. We're going to do them graphically on our calculator. So obviously number 2, the first thing we're going to do is divide both sides, little pointer there, by 4. And that, or by 2, and that gives me 4 to the x equals 20. Now I'm going to put this in y1. I'm going to put 20 in y2. Actually, I don't really want the grid for this one because it's hard to see. And I'm going to have a growth curve, and I'm going to have a line at 20. Because I'm going to have that line at 20, I got to think for a second. I know that it's going to be a growth curve. I know it's got a line at 20. I need to find this point. Now, if all you do is you're just like a drone button presser, you're going to graph it and you're going to be like, oh, my calculator's broken. No, your calculator is not broken. You just typed in the constant function y equals 20. This graph only goes to 10. Press window. Go down to your y max. Change your y max to something bigger than 20, like 25. Press graph. And you see my graph has gotten a little taller here. So there's my exponential curve. There's my line. I'm going to go second, trace. I'm going to pick number 5. Whoops. Uh-oh, I touched something. I'll just start again. Second, trace, number 5, first curve, second curve, and now I'm going to arrow over to where I think it is. So I think it's at like 2 point stuff. Boom. 2.161. Everyone pause the video and try number 3. So for number 3, I'm going to divide both sides by 5, and I get 2 to the x equals 10. And again, this is kind of good that I have already changed my window, because if I didn't change my window, 10 would be like the super tippy top. So here's my line at 10. It's going to be 2 to the x, so it's going to be an exponential growth curve. Let me see. I'm going to change this to 2 to the x. I'm going to change y2 to 10. this is y1, this is y2, and let's see where they cross. There's my exponential growth curve. There's my line at 10. Second trace, 5. I'm already on the first curve. I'm on the second curve. I'm going to move my arrow. Press enter. And I've got an intersection at x equals 3.322. All right, your homework tonight is going to ask you to solve some of these with some of them you're going to solve with your calculator. Homework tonight, we'll go through that tomorrow, but homework tonight, you may use your calculator because there are a fair number of calculations.